hydrogen, an alternative fuel. In this video, we're going to be going over the staghorn corals, a species that lives in the ocean, and how they're affected by the rising CO2 levels in our ocean, as well as how we can reduce these rising CO2 levels using an alternative form of fuel. First off, what's the deal with CO2 in our oceans? Well, one major impact of this is called ocean acidification. This means that the ocean becomes more acidic over time. This is due to CO2 emissions from many different sources, such as the transportation and manufacturing industries. The overall pH of the ocean lowers below 7, leading to many different biological effects, which we will go over. There are a few general effects of ocean acidification. For one, certain organisms have stunted growth. Fish have reduced cognitive development, and it's been shown that they cannot detect predators as well, and that they can't find food or shelter as well. Shelled animals, such as pteropods, cannot produce healthy shells due to carbonate being removed from the ocean, which we'll go over later. This leads to reduced biodiversity, and some species of coral can't grow in these acidic conditions. These effects may not seem very important to humans, however, these effects do ripple off the food chain. As more and more marine life dies out due to lower levels in the food chain being less healthy, then organisms that are higher in the food chain will also lack food. For example, approximately 500 million humans are dependent on fishing, and ocean acidification could severely impact their ability to fish. One major species that would be impacted by ocean acidification is a staghorn coral. Staghorn corals are a species of stony corals, and their scientific name is Acropora curvicornis. They're found in the Caribbean Sea, Gulf of Mexico, and the Atlantic Ocean. They're not quite endangered yet, but they're threatened, meaning that they're quite close to endangerment. This is the food web, showing where staghorn corals fit in the overall ecosystem. As you can see, they prey on small fish and zooplankton, and are preyed on by marine snails, who are eaten by crabs and squid. However, this all leads up to humans, so if staghorn corals begin to die out, humans will definitely begin to feel the impact, even though it's indirect. Here are the effects of ocean acidification on staghorn corals. Polyps, which are the units that make up corals, release argonite, a form of calcium carbonate that forms shells. Keep in mind, carbonate in the ocean is very limited, so it's very difficult for them to form shells from the start. When carbon dioxide enters the water and reacts with the H2O molecules, an acid called carbonic acid is created. This weak acid releases H+ ions, which lowers the overall pH of the water. These H+ ions react with carbonate in the water, which polyps want to use to form their shells. However, when H+ ions react with them, they form bicarbonate. When carbonate is turned into bicarbonate, the overall supply of carbonate in the ocean is decreased. As you can see, here are the equations showing how carbonate is turned into bicarbonate.
So now that we've identified the problem and the effects of ocean acidification, let's ponder some alternative fuels that can be used to combat this issue. Right now, one of the major fuels in development is hydrogen fuel. So some basic information about it is that it can be produced from natural gas, methane, and the electrolysis of water. The gasoline gallon equivalent is 1 kilogram of hydrogen gas, has the same equivalent as 1 gallon of gasoline. The energy content is the amount of heat released when it's combusted, and the lower heating value is 51,585 British thermal units per pound, and the energy content of the higher heating value is 61,013 British thermal units per pound. And this provides a range of how much heat energy is released when hydrogen fuel is combusted. Now, the pump octane number is a number that represents how resistant a fuel is to knocking, which is when the fuel ignites outside of the cylinder. 130 is for hydrogen fuel is much higher than most gasolines, which range from about 80 to 90. In addition, the auto-ignition temperature is a lot higher than other fuels, ranging from 1050 to 1080 degrees Fahrenheit. So a basic overview of the process is hydrogen is either extracted from water using electrolysis or from natural gas using the process of steam hydrocarbon reforming. And this hydrogen extracted is considered an energy carrier. It is fueled into fuel cells, and if it undergoes combustion, it will react with the oxygen to release energy and produce water vapor. So now going into a bit more detail, what is steam hydrocarbon reforming? So it's how most hydrogen is produced today, and what it involves is high temperature steam ranging from 700 to 1000 degrees Celsius that is used to produce hydrogen from a methane source, usually natural gas. And basically what happens in this process is the methane gas reacts with steam under 3 to 25 bars of pressure, whereas 1 bar is equal to 14.5 psi, in the presence of a catalyst to produce hydrogen as well as some unusable gases. So this formula right here shows methane reacting with water and heat to produce carbon monoxide and 3 moles of hydrogen. And then the carbon monoxide is reacted with another catalyst to produce more hydrogen, and which is shown in the second formula. The second method is electrolysis, which produces a much higher concentration of hydrogen that is pure, but it is much more energy intensive. So the process uses electricity to split water into hydrogen and oxygen, and the reaction takes place in a unit called an electrolyzer, which consists of a cathode and an anode separated by an electrolyte. Some of the most common ones are a PEM electrolyzer, an alkaline electrolyzer, and a solid oxide electrolyzer. So what happens in all of these separate electrolyzers, no matter which one you choose, is water reacts at the anode to form oxygen and positively charged hydrogen ions, or protons. Then the electrons from the hydrogen flow through an external circuit to produce energy, and the protons selectively move across the PEM to the cathode. At the cathode, the hydrogen ions combine with electrons to form hydrogen gas, and the anode and the cathode reaction are shown below. So moving on to hydrogen fuel cells, which turns the hydrogen gas into energy that most appliances can use. So they work similarly to batteries, only they do not run down or need recharging. They produce electricity and heat as a byproduct as long as fuel is provided. The hydrogen fuel cells consist of 2 electrodes, the negative electrode, also known as the anode, and the positive electrode, known as the cathode, and the electrodes encase the electrolyte. The hydrogen is fed to the anode, and the oxygen is fed to the cathode. The catalyst at the anode separates H2 into hydrogen ions and electrons. The electrons also go through an external circuit, creating a flow of energy, and the protons go through the electrolyte. The electrons, hydrogen ions, and oxygen meet up and combine to produce water. This process is very similar to electrolysis, but instead it produces usable energy for most household and car appliances. So some of the benefits are the hydrogen fuel itself does not emit any harmful substances, only water and air. In addition, there's minimal maintenance. Again, with the high pump octane number, which resists knocking, it's extremely resistant to heat, and it can also be produced using domestic products, so it does not have to be imported. In addition, the greenhouse gas emissions of conventional vehicles compared to fuel cell vehicles is much higher because the fuel itself produces CO2, as well as the methods to produce gasoline, natural gas, and other forms of fossil fuels. So some drawbacks of hydrogen fuel is it's not very space efficient. It takes up a lot of space to extract a large amount of energy. The hydrogen fuel cells are expensive to produce and are currently limited in their availability. The highly efficient processes of extracting oxygen via electrolysis or from organic matter do not exist currently on a large scale. Only lab tests exist today. FCEVs, which are fuel cell electric vehicles, are expensive and uncommon, and again, are only being used in developmental stages. And while hydrogen itself produces zero emissions, which is a benefit, one of the drawbacks is the methods to obtain it often release some relatively small amounts of carbon dioxide into the atmosphere, but it is still much less than gasoline. So that's it for hydrogen fuel as an alternative, and let's go ahead and stop.